Well, hi, myself B. Chandrasekhar of LE301 of A section. Today I'm going to discuss the topic of gear profiles. And so first we introduce the gear kinematics, and when we discuss about the gearing action, then I'll show you how calculate the transmission values of both transmission values of motion, transmission value of torques. So what is the gear? So a gear is a wait a minute. So a shaft can be parallel or skew shaft. Usually we use gears constant transmission ratios for the but they have very special application. We cannot discuss all. And the gear is normally a toothed element used for transmission of circular motion. Suppose we use many in suppose for in daily life we can see in wall clocks. So here I will show you some pictures of typical gears, and this is spur and helical. So this is the gear axis, and then the teeth are in helixes, so centered to around the center line of the shaft. And these are helical and double helical gears and the helimore gear. These have the helices, but they are contacted, two helical gears put together, and this set of gears are used to connect the parallel shaft. And the next set is spiral bevel Miller straight tooth bevel gears, and these are used to connect two non-parallel intersecting and sometimes not intersecting shaft. So in these examples they are all intersecting shafts, and they are at 90 degrees, and this shaft has intersecting points, and this have different angles as well. And in the third row we have uh, special kinds of gears like planetary gear planetary gear and worm wheel and worm and worm wheel and rack and green. So this is worm and this is worm wheel, and these are non-reversible. So this means that we can only rotate the worm, and hence the produce only rotation on the on gear. So this is the and the rotation of the wheel is output. And we cannot rotate the one wheel and have the rotation of the wall, so the both have to rotate. uh, and finally you have the rack and pinion. The rack can be considered as a gear with various of curvature of infinity and have the pinion. So this is the rack, and when making the prop is a pinion. In the planetary gear we have a pinion, and this shows an internal gear. We can have connected to gears, two external, and we can connect it to the two external gears. And so kinematics of these gears. Let us now come to the kinematics of gearing action. Of the discussion on kinematics will hinge on the very important concept of pitch curve. What is a pitch curve? So what is a pitch curve? It is a theoretical curve which is fixed to a gear. Here there are two machine gears. There are two pitched curves. These curves are such that the relative motion of the gears are represented or cut off, and the rolling of one pitch curve to the other and related to the rolling and skipping, so that represents the relative motion of the gears. that are in mesh. So this is very important to notice that the pitch curve is a curve that undergoes pure rolling motion. So the two pitch curve are with respect to the 1 hour motion, and it represents the rotation motion of the gears. So let's just consider two gears in a mesh and try to look at the transmission ratio. Let us try to understand the transmission ratio, motion transmission ratio of two teeth. So let us say gear 1 has N1 teeth and gear 2 has N2 teeth. So the shown here, we have shown here. So let us consider the number of in a unit time the end teeth which come in contact with the in the contacting zone. So here this is our contacting zone. So if I consider unit length of time, it could be second or minute, that's our wish. Let us count the number of teeth that are passing to the contact. So now because the teeth are in mass, so equal number of teeth will pass through. So let that be. So if you have this as a we have the angular speed of the gear can be expressed as 2 pi by, so omega 1 into AV is equals to 2 pi by N1. So this is nothing but the average, and this is the angle. So N1 teeth and this angle is 2 pi rho n, and similarly this is angles 2 pi by N2, and since the end teeth pass the in a unit time, therefore this expression gives us the average angular speed of the gear 1, and this expression gives similarly gives us the average angular speed of the gear 2, and we have the average gearing ratio of omega 1 by omega 2 into AV is equals to minus N2 by N1. So this is the ratio of average angular speed, which is omega 1 by omega 2 average is equal to minus of N2 by N1. Here I have put a negative sign to stress upon the time that the rotation or repetition, and this sign is very important when we consider the multiple gears, and we will see the instant. However, this expression now we have is now derived is just instantaneous velocity. So instantaneous gearing ratio can fluctuate, it maybe can also fluctuate. So we can have in general omega, the term like this. So omega 1 by omega 2 is minus of minus N2 by N1 plus P into instantaneous. So it is an average value but there is a fluctuation of denoted this P of t is the function which is fluctuation, which is time varying fluctuating constants. 0 mean fluctuating component P of t, and of course, as I mentioned, we would like to motion transmission ratio. So why do we need motion transmission ratio? This is because if we have fluctuating current transmitting ratio, then we have vibration. Then we will have vibrations, fatigue, and the noise. So the gears may be damaged. So if there are fluctuating forces and stretches, they will be fluctuated. So therefore, the gear teeth and the shaft and anything will be under fatigue. So fatigue is a slow and formation deformation, and the load gain transmitter. So the system will be okay. Let us take some time. So that's it. So we have to understand how, under what conditions we can get the constancy of Gaussian ratio. So for that, let us go back to our discussion on Arnold-Kennedy theorem. So here I have a figure of two laminas where hinged at O2 and O3 and O3, so and they are in contact, so we consider that this is some kind of transmission and between 2 and 3, so therefore they expect that this contact will be maintained, and this contact is to be maintained, and for what is the condition for which the follow the contact is maintained. The condition is the relative normal losses between the two bodies acts at the branch, so they must have the same model graph. And let us look at how the Arnold-Kennedy theorem helps us to get a relation of getting at the condition of that must be satisfied in order that the transmission ratio is constant. So now let us recall Arnold-Kennedy theorem. It states that if three bodies are in relative motion, so then the relative ICs and the relative instantaneous of the bodies, they lie on this single straight line. So in this figure, this is the IC between the round and number 1, and the round as we number the round as 1, and the O2 represents the relative ICVT between the 1 and 2, and the OT represents the relative ICT between the 1 and 3. And then in the Arnold-Kennedy theorem, we must have the relative ICs between the 2 3 and the line joining on the O2 and the O3, and this is the treatment of Kennedy theorem, Arnold-Kennedy theorem, I mean. So let us look at the line of the cylinders, and which are drawn. These are drawn here. So how to locate the relative ICs of I2. So let us look at common is the red line is the common normal point of contact. So as I have mentioned, so that this common normal, this is the what is called as so that's the contact as C1 C2 C3, and then now can imagine C1 C2 C3 point imagining C belonging to 3. So these are coincidence points, and that's it, the topic is